All right, folks ready to go? All right, so today we're going to be talking about direct detection of dark matter instead of these astrophysical indirect searches. And so specifically, I'm going to be focusing on the low mass range of axions, which is my favorite. So first, we'll start with a review of just everything from yesterday. Well, not everything, but the how we do these axion photon searches from yesterday. And then I'll also take some of the stuff that I was planning to talk about yesterday, but then we got really into the activity about what actually a dark matter signal looks like in our detector and the different detection regimes. And then I'll get more into this low mass axion range and a couple of different detection techniques. Full disclaimer, I'm a big fan of lumped element detection. That's what I do. But I will talk at the end about what you can do with SRF cavities, although much more briefly. Okay, so to start with review, what are the ingredients that we need to build a detector to look for axions interacting with photons? So you heard this morning about that E dot B coupling. This is the signal that we're actually going to be looking for from that E dot B coupling. And so because of this signal, you need a strong magnetic field to couple your axion to. You need some coupling system to detect this effective current. And then you need a very sensitive sensor because G gamma gamma is so small. Okay, so back to what we missed yesterday of different sources of axions. Dark matter is a very good source of axions for us to actually detect. And so this is what we call a halo scope. So it's basically a telescope looking for the dark matter halo. And the principle is the same thing that you learned about last week, where basically we're on the Earth, you put some detector here, and we're traveling through this wind of dark matter as we pass through the galaxy. And then, of course, in this case, we're going to be talking about looking for axions. So the signal we're looking for is this Primakov effect. Okay, so let's talk about what this dark matter signal actually looks like in our detector, because again, this is your signal. And so basically what you do is you take a time series of whatever sensor you're reading out, and then you Fourier transform it to look in frequency space, because we know that we should have this cosine signal. So it's approximately a monochromatic peak right at that frequency. But I'm going to pose the question to you, why is it not exactly monochromatic? Why is it that when we take this Fourier transform, we're not just seeing a delta function? Exactly. So we're going to be seeing some spread in that signal because there's a distribution of velocities of the axions around us. And this is, again, what you heard about yesterday. So to actually put some numbers on this, I think you heard about it in terms of 10 to the minus 3 yesterday. But if you're thinking about it in terms of actually kilometers per second, we're talking about sort of 200-ish kilometers per second, both for the speed that the sun is moving around the galaxy and also the distribution of the velocities of the dark matter halo itself. And then another number to keep in mind is that the maximum velocity that any individual axion can have is the escape velocity of your galaxy. And so that's just a little bit higher. When you're actually writing down your distribution, it turns out that this is like pretty high up. So really, these are the numbers that you want to be thinking about. So this is under the assumption that we're only going to be seeing one axion at a time. There could be many axions. In fact, if you believe string theory, they'll say there's lots and lots of axions out there. But any individual peak will be one peak unless you have them all like very closely spaced. But then, of course, there's some distribution, right? And I think, no, I'll have that in a second. I'll have a picture of what that distribution actually looks like in a moment. Does that answer your question? Okay, great. Okay, and then I think I don't really need to cover this in detail because you heard about this before, but because we have this low velocity dispersion, it means that we have this nice coherence time that we can average over to ring up a signal. Okay, so there's that shape that I was talking to you about. So this is what the signal actually looks like in our detector. So like I said, you take a time series of your data, and then you Fourier transform it. And then you end up with this Maxwell-Boltzmann distribution if you have just a simple standard halo model where you have this virialized dark matter. So at the bottom end of this is the axion mass, or equivalently whatever the frequency is. And then the spread here is determined by that velocity dispersion. So again, this is for one axion mass. You could imagine that if there are many axions, you could see multiple of these peaks. But the most naive thing you look for is just this one peak shape. And then of course, one thing to note is that this is going to be a persistent signal, right? Because we're constantly going through this field of axions. We don't expect the axion mass to be changing over time. This should be relatively constant with some caveats, and I'll talk about that in a second. Okay, so here's one of those caveats. If the axions are actually clumped rather than being perfectly distributed, you no longer will have this persistence condition, right? So say you have axions that are in clumps that the Earth is traveling through. Sometimes you'll have a higher intensity and sometimes you'll have a lower intensity. And so you could imagine this peak sort of going up and down depending on how many axions you're traveling through at any given time. That's that rho dm figure, right? And so when we're building an experiment, we kind of hope that we don't have this clumpiness because we have a resonant experiment. We want to see this signal persisting over time. You want to be averaging coherently, but it is possible that things could be clumped, and that would actually be quite a challenge for detection. Okay, and then again, you heard about this a little bit this morning, but there could be variations to the standard halo model. So we know for a fact that there are streams in our galaxy. So basically, over the history of the Milky Way, there were various galactic mergers, smaller galaxies, bigger galaxies all merging in. And as they they fall into our galactic sort of gravitational well, they get pulled apart. And so that's what you're seeing right here. You can see basically you have these streams as these galaxies get torn apart, and you can track the position of these streams by mapping the stars out, but we know that those galaxies would come along with a dark matter halo that is also getting pulled apart in this stream. And the interesting thing about streams is that they actually would have a lower velocity dispersion than the dark matter in our virialized halo. And so if you think about that, what actually does to your dark matter signal, if you had some sort of virialized halo, and then you also were sitting inside a dark matter stream, you would have a very sharp peak because there would be less spread in the velocities of that subcomponent of dark matter that's coming from the stream. Yeah. Yeah, so fundamentally this would, like, you could have some component that was at this mass, but if you think about the velocity distribution, if you have most of the dark matter in that stream is moving very quickly relative to us, it would be shifted up. So this distance here would be the relative velocity between us and the stream. Other questions here? Okay. So one thing to note, right? So in this picture, I've drawn it where the stream actually has a higher amplitude than this virial halo. And it could be that. It could also be lower, depending on how much dark matter is either in the halo or in the stream itself. But because this is really narrow, you don't actually have to have as many axions in it. If you think about integrating under that curve, this could actually be a stronger signal to look for than that standard halo model shape itself. Okay, so other things that we could be seeing in our signal is modulation with time. So we know that the Earth is rotating and that it's traveling around the sun, and that's changing our velocity relative to this dark matter halo. And so this is an example of what that signal shape would look like over the course of a year. And you can see basically it's going to shift both in the average velocity and in the amplitude as you travel, so as the Earth travels around the sun. Okay, so that's everything I want to say right now about the dark matter signal. I want to go back to this plot that we talked about yesterday, which is, of course, the coupling strength of axions to photons versus the axion mass. And I want to break this down into different regimes. Because we have many orders of mass to cover, you have to have very different detection techniques to look for dark matter in these different ranges. And again, yesterday, we were talking about these astrophysical searches where a lot of the times the axions we were looking for were sort of boosted, right? They had a large velocity because they're being created from the inside of a star or whatever. And so basically you could look for a certain energy and it would cover a large range of axion masses, whereas the axions we're looking for right now are coming from the dark matter halo, and so they're relatively at rest. And so we're really looking for that rest mass energy. And again, you'll hear a little bit more this afternoon about why it is that they're at rest, but keep that in mind. We're looking right now for axions that don't have a lot of extra sort of kinetic energy. Okay, so the first region that people looked in was this intermediate mass region at around a micro eV. And so you can see right away from this plot that this is where the most progress has been made in terms of actually searching this well-motivated QCD axion band. And the really nice thing about this intermediate mass region is that a micro eV axion has a wavelength that's about the size of a person. And the reason that's really nice is because then you can build a tabletop experiment to exploit boundary conditions on your wave. So it's this sort of happy coincidence. People also thought there was really good theoretical motivations there for a while. It turns out this entire band is very well motivated, but people were very excited about that. A long time ago, basically, Pierre Sakivi came up with this idea that you could use a cavity to exploit these boundary conditions. And so this is what that looks like, right? You have some cavity, you can basically line up the nodes of your axion wave with the walls of your cavity, and then you can get a resonant enhancement in your signal. And I think you'll hear more about that tomorrow. Okay, so this technique works really, really well. You can see it here because there are these exclusions. But this cavity technique does not work at the high mass and low mass ends of the spectrum. It's just really not practical. So first, if you think about going up to higher masses, if you wanted to keep using this cavity technique, you would have to create very small cavities because the wavelength is getting much, much shorter. And at first glance, that might be fine, right? You could create smaller cavities. But the problem is that you're reducing the amount of dark matter inside your detector. And so that's immediately reducing your signal. So instead, you can come up with other ways to look for these high mass axions. So there are a couple of different ideas that you can think about. I work on a reflector experiment where, again, you're basically exploiting the fact that the wavelength of your axion is smaller than the size of your experiment, and you can build something that looks like a telescope. Okay, people also think about things like dielectric stacks. This is a way where you can still basically have this resonant enhancement, unlike the reflector where it's generally at least a little bit broadband. But yeah, this is an idea that works above the regime where cavities work. Okay, now going to low masses, once again, cavities are not practical. Now we're talking about wavelengths that are maybe kilometers in size or hundreds of kilometers in size. So cavities have been built with this size. This is basically what LIGO is. But LIGO is a very expensive experiment. And they also didn't have to have a magnetic field covering that entire cavity. So instead, we're going to make use of this assumption that the wave is much larger than the size of our detector. And so we can assume that basically our signal is in phase across the entire thing. And so what you can do is you can build what's called a lumped element experiment. And this looks basically exactly like a radio. So if you think about when you have your radio, you have this tank circuit made of an inductor and a capacitor. Those are lumped circuit elements. And the assumption when you're putting your antenna up is that the wavelength is larger than the size of your L and your C. There are, like I said, some other ideas out there for detecting low mass axions. So superconducting radio frequency cavities is another idea. This is using a cavity, but the cavity is not tied to the size of your wave now. And again, we'll revisit that later. So 3 different regimes. The wave is either the size of your experiment, much larger or much smaller. And we need very different techniques, both to couple to our signal and also for the sensors that are actually going to read this out. So I think the analogy that I like to use here is you wouldn't use like a radio dish to detect gamma rays, right? You need very, very different kinds of systems in order to detect these different wavelengths of axions. Okay, and you'll hear all about all of these this week, but today we're going to be talking about the low mass end. So I think, yeah, any questions here about these different ranges before I talk about some other sort of general considerations when you're building a dark matter experiment? Yeah. Yeah. So these boxes are notional, I will say. As you get to really, really low masses, because this band is falling really low, it gets really hard to build an experiment that can actually probe inside this QCD band. So I haven't seen any projections for experiments much below sort of around here, like in the sort of 10 to the minus 10 to the minus 11, that can actually realistically probe the QCD axion band. Obviously, there's some ideas for other kinds of, so this is a super radiance bound, but those are pretty model dependent. Okay, yes, Casper can look at lower masses, but not looking for the coupling between axions and photons. And so I think Sergio is going to talk about this. Sorry? Yes. Yeah, again, Casper does say it can reach the QC axion line, but not looking for the axion-photon coupling, looking for like the nucleon coupling. Yeah. I think there was another question. Yeah. Sorry? Clump? I couldn't understand. Lumps, yes, lumped element. Yeah, that's okay. Yeah, no clumps of axions here, just looking for standard halo model axions. SRF is superconducting radio frequency cavities, and I'll talk about that at the end. Okay, so let's move on. So another general consideration for dark matter searches. So you can read them out in different ways. You can either read out in broadband, where you're looking for many frequencies at once, or you can read out with a resonant detector, where you're only looking for a small range of frequencies at once, and then you scan. So what is the advantage of a broadband detector? Well, I think it's pretty obvious. You can look over a wide range of frequencies at once, right? But the problem here is you don't get any sort of resonant enhancement. So the nice thing about a resonator is that you can actually boost your signal by ringing up a resonator. And you can get a really, really huge enhancement because you expect to be able to build resonators with very, very large quality factors. So I wanted to narrow down a little bit on what I actually mean by quality factor, because this is really important to really understand what this means. There are a couple of different definitions for quality factor, and they're equivalent. So the first one you can think about is basically how much energy can be stored in a resonator compared to how much energy is lost in each cycle. So by each cycle, it's basically depending on what the frequency of your resonator is. So the reason this definition is really nice is because as your axion is ringing up your resonator, that's telling you how much energy you can ring up coherently before you start to lose it to the environment, right? So if I have a quality factor of 1,000,000, it means I'm getting 1,000,000 times enhancement in my axion signal before it's being lost to other things. The other way of defining quality factor is this F over delta F, which is the frequency over the bandwidth. The reason this is important is because this is telling you what bandwidth you're looking over as you scan over the different axion masses. So if you have a higher quality factor resonator, it means you're looking over a narrow band of frequencies, which means to scan over a certain range of masses, you have to take more tuning steps. So there's an inherent trade-off, right? You get more enhancement if you have a higher quality factor resonator, but you're looking over a narrower bandwidth. Now, this definition of quality factor is specific to a passive resonator. So if you have active components, you can basically lose these restrictions where you can only look over a small bandwidth if you have a large enhancement. But I believe all existing axion experiments use passive resonators. There is R&D underway that I'll mention again later, where people are trying to think about how you could use active components to improve this. Because one of the hardest things about axion searches, again, is that we don't know what the mass of the axion is. And scanning takes a very, very long time. Yes. Yeah, great. Basically adding energy to the system some way. So a passive component is something like an inductor or capacitor. An active component is something like an op-amp. Maybe op-amp is not a good word for talking about that theorist too, but an amplifier where you're adding energy, like pumping the system, right? So like if you're thinking on a swing, you like pump your legs and you're adding energy to the system, that kind of thing. Okay, does this make sense? This is really critical for understanding how these experiments work. So if people have questions here, you should ask them now. Okay, and you can come back and ask questions about it later too, as it becomes more concrete. Okay, so which one should you pick? Most experiments opt for resonant detection. And the reason for this is because the signal is tiny, so if you can enhance it any way you really want to. And particularly if you're trying to reach into the QCD band, that's really, really low GA gamma gamma, and so you want to enhance your signal. But I do want to sort of just call out that broadband experiments can be really valuable. I think sometimes they're undervalued in the community, particularly if you're building an experiment that's looking for axion-like particles that doesn't have a hope of reaching the QCD axion band. We don't really have a prior on where ALPS should live in this parameter space. And resonant experiments are really complicated. Tuning is very challenging and often very expensive. And so you can basically search the same area of space. It's just wider instead of deep if you're looking for ALPS. And so that can be really valuable. And then the other thing that makes broadband experiments really nice is that if you do have clumpy dark matter and you have a transient signal as we're traveling through a clump, a broadband experiment would actually be able to see that. Whereas a resonant experiment, you're only looking at one frequency at a time. And so if you happen to not be tuned to the correct axion mass as you pass through a clump, you're totally missing that signal. So that's my argument for broadband experiments, and I'm going to tell you about all the work I'm doing with resonant experiments. But I think that it's really important that we really consider these options as you're designing your experiment. Okay, so the rest of today, I'm going to be focusing in just on this low mass detection regime, but the things that I talked about the dark matter signal, about broadband resonant, those are all valid for the full mass range. Okay, so first, lumped elements. And I wanted to put just a little bit of motivation. You're going to hear more about the sort of production mechanisms and cosmology later, but I just wanted to put a few things about why you might choose to look for low mass axions versus other mass ranges of axions. So from field theory, basically, if you put your high energy scale at the gut scale, you're going to end up with low mass axions. So there's a good reason for it. Also, if you believe in string theories pretty much universally predict one or possibly many axions, and typically at these lower mass ranges. And so I was just talking with Sergit about this yesterday, but many of these theories predict sort of a model-independent axion, so it doesn't matter which string theory you're looking for, or which string theory you're writing down. They predict an axion also around a nano-eV. And then one thing is if you actually were to discover axions with one of these experiments, you could constrain the sort of landscape of string models. And then finally, from a cosmological perspective, one thing that people sort of didn't understand for a long time is that you actually can very naturally create the correct abundance of dark matter with these low mass axions. And I might talk about this a little later if it doesn't get covered in the other lectures about why that's true. But I just put a selection of many papers about people saying that this is the right mass range to look. Anybody who builds an experiment will tell you that there's the correct mass range, but this is definitely the correct mass range. Okay, so this is the program of experiments that I work on. So Abracadabra was a prototype experiment that proved that the lumped element method actually worked. It had placed some limits right here. And then ever since we placed these limits, there have been several other experiments that have popped up also demonstrating the feasibility of this method. And now we have a program of different experiments that's trying to probe all the way down to the bottom of this QCD band using this lumped element technique. Okay, so when I was talking to you about how we have these long wavelengths, basically the signal's in phase across the entire detector, which means you can actually write down your detector as a circuit diagram made of lumped elements, because the assumption that you can talk about voltages and currents is correct, rather than thinking about sort of waves with phases. So this is the entire lumped element detector in circuit diagram form. And what I want to do is I want to step through these different components of the circuit diagram, and then I'll come back and put it in the context of an actual detector. And I just want to note that those three ingredients that I talked about at the beginning of the lecture, a magnetic field, a coupling system, and a sensor, are all included in this diagram. So the first thing you need is you need that magnetic field. That doesn't fit nicely in the circuit diagram form, but the result of the axion interactions with the field is a current. And so you can just draw that as a current source in your circuit diagram. Then you need ingredient number 2, which is some sort of coupling system. And you can do that via a transformer coupling. So basically you take this effective current and you inductively couple it into real wires. And then you end up with a real current that is circulating in real wires. Okay, so that's very nice. You now have a real current to detect. But this current is very small. And so that brings you to ingredient number 3, which is a very sensitive current sensor. Okay, and so in this diagram, I've drawn it as a squid, but it could really be any kind of current sensor or amplifier. And then the last thing is that you basically read that out as a time series, Fourier transform it, digitize it, and save it for offline analysis. Now, I want to point out that this circuit diagram that I showed you is actually a broadband search, right? It didn't matter what the frequency was of that signal. All of those signals could equally well get through to our digitizer. So what we want to do, if we're trying to look for the QCD axion, is enhance our signal with a resonator. So what we can do is we can turn this central element into just an LC resonator by adding a capacitor. That's really nice. Okay, so we've demonstrated resonators with quality factors of about 2 million. So now we can get a 2 million times enhancement in our signal. But again, we don't know what the frequency is of that signal, and so we need a tunable resonator. So we add some sort of tunable capacitance here to be able to scan over those different frequencies. I do want to note that this can be achieved with multiple geometries, and I'll come back to what those geometries are in a moment. But I'm going to basically show what this looks like in the context of a solenoidal geometry, and then I'll talk about what this looks like with a toroid as well. And the reason I'm going to show it to you with the solenoidal geometry is we're just about to start an experiment where we're building a solenoid at Berkeley that we're calling CAL for Cal Axion LC experiment. I really like nested acronyms. So this is what this looks like in the context of the solenoid. But basically, if you take that solenoid and you wrap it around, then you get the same effect with your toroid. Okay, so we have a solenoid. It has a magnetic field in the z direction. If axions exist, they will interact with it and they will create an oscillating effective current, also in the z direction. If you have an oscillating effective current, you're going to get a real oscillating magnetic field going around. And so the way we want to couple that into our system is with that transformer coupling. So we need some sort of pickup loop to basically catch that flux and turn it into a real current. Now you can imagine just taking like a loop of wire here, but it turns out that it's better to basically rotate this azimuthally and make a full coaxial detector. So it's basically a loop of wire that's been rotated around. And the reason for this is because you end up with currents that are on the inside of a coaxial structure that cannot interact with any lossy materials that are in the magnet. When you build a magnet, you really have to have lossy materials because you have to cool it down somehow. So you need lots of copper and lots of glue and all sorts of sort of ugly things that you don't want your axion-induced signal to be seeing. And so this coaxial structure allows you to hide that current from all of those materials. Okay, so now we have a real current that's circulating on the inside of this pickup structure. And then we want to couple it to a tunable capacitance, which I've shown right here. And then we need to couple it again to our sensor. And so for the current iteration of sensors, we use something called squids, which are superconducting quantum interference devices, not those kinds of squids. Yes, yeah. So you cannot cover like multiple decades in mass with a single resonator. You do have to do swap outs if you're going to be covering a very large range. Other questions here before I move on? Yeah. That's the magnet. So this red, yeah, sorry, this is a little unclear from this picture, but basically this red thing is a magnet. So there's superconducting wires that are strung around like this that carry current that creates the magnetic field in this direction. Here, let me just step back. Actually, I think that'll make it a little more obvious. So we have a magnet. It has real wires that are circulating current like this to create a magnetic field in this direction. And then inside the bore of that magnet, you place this coaxial pickup structure. Exactly. Yep. Yeah. Did I see another question? No? Okay. Yeah, so this structure can cover a wide range of masses as long as the wavelength is longer than the size of your detector. So it turns out that you can actually extend close to your wavelength being the size of your detector, but it starts to look a lot more like a cavity. And so you can start having things where basically, instead of just having a voltage here that's, you can think of as the voltage that's induced by like a current actually circulating, you can start to think basically there's going to be modes inside this cavity. And so sometimes, despite the fact that you have a signal, you're actually going to have no voltage across there. And so you'll null out your signal. Oh, you absolutely could. It's just that you don't have any sensitivity to QCD axions on there. And as Sujit was talking about, and I'll mention later with some numbers, as you go down to these really low frequencies, if you're building a resonator to search for it, you'd have to ring up your resonator for a very, very long time. So it's just, you would have very little sensitivity. Yeah, so if I go back, here we go. So I can tell you right now for abracadabra, this lower limit was actually because of vibrational noise. So as you go down in frequency, mechanical vibrations become more and more of a problem. And so our sensitivity just started rapidly falling off there. And we do expect that to potentially be an issue for some of these other experiments, although now that we know more about how this works, we can mitigate that to some extent. But yeah, you start to run into issues, noise at low frequencies. But fundamentally, there's no problem other than the slow scanning speed. Yeah. As a what? It's not a trigger. It's basically enhancing your signal. So what's happening is your axion wave is oscillating, right? And so it's slowly ringing up this resonator with power, and then you're taking the power out of your resonator. Yes, yes. So there's various sources of noise, and I'm going to talk actually more about this tomorrow because I'm going to talk about some of the sensors that we use. But basically, depending on where the noise enters your system, it could be rung up by your resonator also, but it could come farther downstream where it's not interacting with your resonator at all. But your noise is not going to be coherent, so you can average it down to some extent. Yeah, but with a big caveat that there are thermal noise as a fundamental limitation. That's the fundamental background that we have. Okay. All right, so like I said, there's a couple of different options for the geometry that we choose for our experiment. So I showed you this solenoidal design where you have the B field in the Z direction, but actually all of so the experiment that we did already, aber 10 centimeter, and also the experiment that we're about to get data from, DM radio 50 liter, uses a toroidal design. And there's actually some pretty interesting trade-offs between these two different geometries. It's not sort of how I simplified it before, where you just wrap your magnet around. And I'm going to talk about some of the sort of pros and cons of these two different geometries. So the first thing that you really need from whatever experiment you build is a high quality factor. And you can get this in different ways with these two different geometries. So first of all, with a toroid, if I go back, you can see basically your axion current is here, inducing a magnetic field in the center bore. So you're reading out your signal here where you're in a field-free region. And the nice thing about that is you can use normal superconducting materials to pick up your signal, which inherently have less loss, right? So you can automatically sort of gain an improvement in your quality factor by using superconductors. This also means that you potentially, sorry, actually, never mind, let me not say that. But okay, moving on to the solenoid. So because you have your pickup inside your high field region, you can't use normal superconducting materials because they don't stay superconducting in large magnetic fields. So the most easy thing to do is basically use something like high purity copper, and that will reduce the quality factor. But you do have this nice thing where you have your currents fully enclosed inside your coax, which you don't get for this toroidal design. So you have this trade-off between what materials you can use and how your currents are sort of sampling the lossy materials in the environment. One thing to note for this solenoidal design is that there is a possibility that you could use some high temperature superconducting materials because they can stay superconducting in high magnetic fields. But that's sort of speculative. We haven't proven that this actually works with the LC resonators. Another thing is that you want a large frequency reach. So the problem with the toroid in this aspect is that it actually cannot reach the highest frequency range that this method can get to. And the reason for that is if you think about the frequency of an LC resonator, F equals 1 over the square root of LC, if you have any parasitic L or C, that will put a fundamental limit to how high you can reach in frequency. And this toroidal design is more prone to parasitic capacitance than the solenoidal design is. Basically, you have to have a way of shielding that central pickup region from your magnet. And the way you do that requires you to have sort of layers of superconducting material that are just going to have some capacitance in them. And so a reason to use the solenoid is that you can avoid a lot of those parasitics. Random note is that you can also use the detectors to detect gravitational waves. Solenoidal designs are much more sensitive by orders of magnitude to gravitational waves than axion detectors. This is secondary science. I'm not going to talk about this anymore, but this is a really nice thing about solenoidal detectors. Okay, this is a very practical consideration. You have to build a magnet to get an axion signal. Solenoidal magnets are very common. So if you've ever had an MRI before, that's a solenoidal magnet. You can get these magnets off the shelf. Toroids are much less common, and so you generally have to get them custom made. And a big part of the cost of building a magnet is actually making the apparatus to wind your magnet. And so anytime you have this sort of custom design, it's going to increase the cost of your magnet. That being said, all of those considerations that I told you are true for these sort of smaller scale experiments. As you go to larger scale experiments, you're going to have to build a custom magnet. And so maybe some of those trade-offs are not as significant. And so one thing that we've been working on in my group is basically figuring out what some of those sort of cost trade-offs are and figuring out how you can get the most bang for your buck in sensitivity. And then the last thing about the magnet is safety concerns. So again, as you scale up, these magnetic fields contain a ton of stored energy, a lot of energy. And so you really have to consider what the forces are. And in the case of a quench, where basically your superconductor goes normal, there's going to be a lot of current that has to be dumped somewhere. And so you need to think about the considerations for safety, both of the equipment and also the people that are operating the experiment. And a nice thing about the toroid is all of those fields are contained inside the toroid. There's no fringe fields like there are with a solenoid. And so that helps you mitigate some of those safety risks. Okay, and then I want to pose a question to you because you were talking about sort of axions and dark photons this morning. Can both of these geometries be used also to detect dark photons? If you want to take a moment to talk to the people around you to figure out if you can figure it out. You don't. So take the magnet out. You have a geometry. I can go back to here. Can you use the detectors to look for dark photons? Why don't you talk amongst yourselves? Figure it out. Hmm? Huh?
This frequency. Actually also get this kind of current for a long way.
Yeah. Yeah. Yeah, so for the same, if you're using the same detector, the same exact pickup structure, just take out the magnet, can you detect a dark photon at the same frequency that you can detect an axion at? Does anybody have any ideas? Does anybody want to tell what they've been talking about? Anybody figured it out? What's the difference between an axion and a dark photon? People know that one. I know that they know the difference. What's the difference between an axion and a dark photon? Sorry? Yeah, that's true, but why is that? Why can you have this kinetic mixing?
In terms of things shown in this picture, what would be things?
More fundamentally, like the particles themselves, not even thinking about their interactions. What's different about an axion and a dark photon? Totally, exactly. So what's different about if you have a preferred direction? Yeah. So dark photon also is massive. Yeah. Okay, I'm gonna spoil the fun because I want to move on. But if you think about having a preferred direction for your dark photon, this experiment, if you have a preferred direction, say you can have your vector pointed in the direction of your solenoid, you can use this same detector to look for dark photons, right? You can think about your sort of oscillating E field this way. For the toroid at the same frequencies where you have long wavelengths and you have a preferred direction, if you have a signal that's going across your detector, say this way, you're actually canceling out your signal because you have it going in one direction this way and one direction this way, and therefore you don't have a net current traveling all the way around. Does that make sense? Okay. So if I have a preferred direction and I have a toroid, for my axion signal, the direction of the current is the same direction. It's the same direction as the field, right? It's oscillating coherently. So you have a current that goes all the way around inside your toroid. For your dark photon, there's no magnetic field. So for the same pickup structure, you can think about it's oscillating like this, which means you have a cancellation on the other side of your toroid. So if you want to use the exact same detector to look for dark photons, you need to build a solenoid, not a toroid. Now, it turns out you can basically change the geometry of your pickup structure for a toroid so that you can have your dark photons oscillating in the z direction, and then you can make it work. But you have to have a different pickup structure. So you'd have to have a hardware swap out, which again, it's expensive if you're building an experiment. Okay, I'm going to keep moving. Okay, so I told you all about our detector, but basically this is all of a way of reading out an enhanced signal in a time series, and then again, you Fourier transform it. And this is what you get out. So this is real data from the Aber 10 centimeter experiment. And so you can see on the y-axis, you have basically power in your digitizer versus the frequency of your signal. And just to orient you, the nano-EV axion is around here. So what do we actually need to do to process this data and turn it into either a detection or a limit on GA gamma gamma? So the first thing you see when you're looking at this spectrum is that there's a bunch of peaks. Unfortunately, those are not all axions. Those are backgrounds. So the first thing you have to do is you have to go through and remove any backgrounds that don't look like axions. Okay. Then what you need is you want to have some sort of either, again, limit or detection in terms of the coupling constant, GA gamma gamma. And so you need to calibrate your detector. So you need to turn this power in terms of volts squared per hertz into GA gamma gamma. And then lastly, you're going to have a calibrated spectrum with all of your backgrounds removed. And so you're going to basically take your template for your axion signal and scan it over your frequency range to see if there's any fits. Okay, so I want to tell you a little bit about calibration. I'm going to tell you a little bit about background rejection. So the first thing is, how do we actually calibrate these detectors? And when we're thinking about a calibration, we need to think about what is the information we actually need to extract from this calibration. So fundamentally, like I said, we need to take our DAC voltage and turn it into GA gamma gamma. But there's a lot of pieces that go into that. And some of them are the ones I listed here. So you need to know what the frequency is that your resonance is on. If you don't know what that frequency is, you're not getting the right thing. You also need to know the quality factor of your resonator. You need to understand how much your signal is actually being enhanced. You want to understand the gain of your full system. So as you go from an axion to a voltage in your DAC, what is the actual sort of like gains along the way? And then another thing you can think about is the gain of your readout itself. So not of the axion coupling to your detector, but of the sort of amplifier systems. Now, all of these are sort of entangled with each other, right? Some of them are subsets of the other. But it turns out calibrating these detectors is hard. So you can extract these things in different ways, and then you can sort of use this sort of matrix of parameters to finally extract this thing that you really want. So what we really want to do is we want to inject a tone of a known amplitude, and then we want to see what we get out. And so we want to think about where in our detector we can inject this calibration signal. We also want to think about what different frequencies we might be interested in injecting those signals at. And then also I'm going to say sort of what shape of signal. So does it have some distinct time signature or some distinct signature in frequency space? So the first thing is, where can we actually inject calibration signals? So you can either inject it right where an axion enters the system. That's the best thing. That's how you could do a full end-to-end calibration of your system. Unfortunately, you can't leave a calibration loop inside your detector while you're running because this is going to spoil the quality factor of your detector. Basically, all that signal, instead of being enhanced resonantly here, is going to be leaking out into that calibration loop. So you can do this nice calibration where you do that full end-to-end gain, but then you have to take your calibration loop out, and then you're basically flying blind while you're operating, and you don't want to be doing that. So we have a couple of other different ways that we can also calibrate the system, but it's not a full end-to-end gain. So you can inject into your resonator with a very weakly coupled port. So you will have some loss there, but by having a very weak coupling, you can decrease that loss below the sort of inherent losses to the environment. And then you can also calibrate just your amplifier system. So you can inject a tone into your squids, for example, and then see what you get out.
Then you have to remove it. Calibrate, open source of the
Right. So you want to basically make sure that you have stability. So you want to make sure that your gain stays constant over the time of your run. And this is especially important for a resonant experiment because you're tuning your resonant frequency over the length of your run. And you don't know for sure that that system gain is going to be the same as you scan over the different frequencies. Yes, you do. But again, you need to have a very good understanding of what the frequency is that you're sitting at and the quality factor at each point. Maybe you're in a period of time where they're doing construction in the building next door, and so there's more vibrations. Maybe there's some extra losses that are happening from that. In an ideal world, you calibrate, take the wire out, run your detector, no problem. In the real world, it's not so simple. Okay, so this is what that sort of what we call a mimetic axion looks like in real life for a toroidal detector and a solenoidal detector. So basically, you're trying to mimic the form factor for an actual axion signal as much as you can. So for a solenoidal detector, remember we have our axion current going in the z direction. So basically, you can thread a wire through your detector and you can inject a signal that way. In the toroidal detector, your axion signal goes around like this. So again, you thread a wire inside your magnet, but then you take it out. You can also think about what different frequencies you inject at. So there's a few different options here. You can not inject at all. You can just read out the thermal noise of your system. So we talked about that just a moment before. Basically, there's going to be some fundamental thermal noise that will describe the shape of your resonator. And you can basically just average this. It's the same thing as your signal, but we're calling it a noise right now. And you can see what the resonance frequency is and also what the quality factor is. And if you know very well what the temperature of your system is, that actually gives you a calibration of your system gain. Unfortunately, this is not a very precise way of measuring this because it's noise. So you'd have to average for a very long time to have a good understanding of what those parameters are. So you want to also be doing other kinds of injections. So you can inject signals in band. You can also inject signals outside of the resonance bandwidth. And both of these injections give you an understanding of what the response is of your system. And then the last thing is the shape of your signal, so what signatures you can inject. So you can just inject monochromatic tones, and that gives you just a gain. So you can either do like a scan across your resonance with a bunch of monochromatic tones, or just inject on the sidebands. If you're injecting in your resonance band, you don't want to do that while you're operating for physics. But if you inject in the sidebands, you can actually do that at the same time that you collect physics data because it's outside of your frequency range of interest. And so that's a really nice way of having really real-time calibrations of your response. The best way to figure out what your resonance frequency and quality factor is with a ring down measurement. So basically you inject a signal very close to resonance for a long time, and then you turn off that signal and you look to see the resonator itself ring down. And that gives you a very precise understanding of what that quality factor is. Remember, it's the sort of energy stored in the resonator over the energy lost per cycle. And so you're really just actually counting how much energy is lost per cycle. And then the final thing is a synthetic axion signal. So far I've told you about what you can do with a monochromatic tone. The axion signal is not a monochromatic tone, so you may want to see how your system responds if you have that range of frequencies. This is less valuable for calibrating and more valuable for blinding. So if you want to inject a sort of a fake axion signal while you're running, you can make sure that you're reproducing it in your analysis at the right amplitude. Okay, and now I want to talk just briefly about background rejection. And so I'm going to pose to you what is different about the axion signal than the various sources of background that you might have in your detector. How can we discriminate between backgrounds and axion signals? Any ideas? There's lots of things that you might think of as ways that we can discriminate. So that's true for this thermal noise background, but not all of your backgrounds are just thermal noise. There may be other things as well, but that's a very good point. Yeah, that's one of them. Yes, yeah, it's a persistent signal at a known amplitude, for sure. Any other ideas? What's distinct about the axion signal in our detector? That's another way of thinking about it. Yeah? You mean basically seeing that Maxwell-Boltzmann distribution? Is that what you mean by like asymmetry in frequency space? Okay, yeah, exactly. You have a known shape for your axion signal. That is a way. I mean, known, right? There could be different signals, but we do have a shape that we expect for our sort of most basic analysis. So the signal is also electromagnetic. You hope not. You hope you can shield out your backgrounds that are really, really high. So there can be some backgrounds that leak in that are at the same magnitude as your axion signal. Okay, well, you have talked about a lot of those things. So the first thing is it has an expected line shape that we can look for. And it is persistent over time with a known amplitude and frequency that doesn't change. Even if you take data for a while, go to other frequencies, and then you see something, and then you rescan that spot, you should see at the same amplitude at the same frequency. Another way that you can discriminate between an axion signal and potential sources of electromagnetic interference, for example, that are coming in later down in your signal chain, is that the axion signal should roll off with your resonance. So if you see a potential signal and you scan your resonator over that axion signal, you should see that amplitude go up as you're on resonance and down as you're off resonance. Whereas if you have some sort of signal that's coming in, say, from your amplifier, you don't expect to see that. A really, really valuable way that we can discriminate is that we know that the axion signal scales with the magnetic field. So if you have something that satisfies all of these other things, what you can do is you can ramp down your magnet and you should see your signal scale proportionally with that magnetic field. There are very few backgrounds that you expect to do that. The only backgrounds that would do that are backgrounds that are associated with the magnetic field itself. And then the last thing, say you have a background that's coming from a magnetic field, you don't expect it to be modulating on a sort of daily and annual basis. And so one really nice thing about these axion signals is that it's really hard to think of backgrounds that you can't reject, you can't veto by following all these different criteria. In fact, I don't think that there have been any axion experiments that have ever found any backgrounds that have satisfied all these criteria, or else they would have published a discovery paper, right? This is very different from a WIMP signal, right? Where you expect to have a lot of these backgrounds that are coming from like radioactive decays and things like that. And so you really have to do this statistical argument where you're trying to reduce your backgrounds as much as possible, but they look very similar to the signal that you're seeing, that you want to see. Yeah, sorry? Yeah. Yes. Yeah. So that's true about WIMP signals as well, is that you do expect to see annual and daily modulation. But they don't have all of these nice other vetoes as well. So if you have sort of environmental effects, I mean, this is what happened with DAMA, right? Is they're seeing this modulating signal, but it's not a dark matter signal. Other experiments have vetoed it, but they don't know where it's coming from. There is layers of like Faraday shielding. Yeah, so in my own lab, we have this magnet, and you basically have to tape out a line because there is going to be magnetic fields that are spilling out. But you don't have to worry as much theoretically about like electromagnetic interference. I'll come back to that. It turns out it is important, but you do have layers of shielding to try and reduce stuff coming in. You do have to worry about other signals, but they don't scale with the magnetic field. Is that what you're asking about? Um, so the kinds of backgrounds that you can think about are things like if you have stray magnetic fields that are vibrating through your pickup, that would scale with a magnetic field, right? But it doesn't have that signature line shape. It doesn't modulate. It's not, I guess it would roll off with the resonance. But yeah, so it's something that you can veto with some of these other things. Other questions here? Okay. So we had a bunch of backgrounds in Aber 10 centimeter. I showed you all those peaks. I just wanted to talk about one of them because I think it's pretty cool. Aber 10 centimeter and all these lumped element experiments are in the AM radio band. And so we did not have enough shielding in this first prototype experiment to fully shield out radio stations. And so we could actually, we had an undergrad write a script to demodulate the data, and we could listen to local radio using our data, which is kind of crazy when you think about how many layers of metal shielding we had around it that we could do this. This really demonstrates just how sensitive these searches are. So this is 14:30 a.m., which was a local station in Boston. And so you can see right here, I don't know if something's wrong with their antenna or if it's normal for it to be varying around in frequency so much, but these are all at known frequencies, so they're very easy to veto, but that proves to you that you really have to be careful about shielding and that you really want all of these different ways of vetoing backgrounds. I'm sorry? Why does the vibration use the what? Current. Oh, how does it induce a current? So if you think about the axion signal itself, right, you have some oscillating magnetic field. If you have a vibration of your magnetic field, it's also creating an oscillating magnetic field in your region of interest. So it doesn't have that signal shape, but it will create some background. Okay, so coming back to the experiments themselves, you can see that we have lots of different projections on this plot. And so you might be asking yourself, why are we building so many different experiments? So it's a good principle for when you're building experiments to do these staged approaches. Basically, you figure out what the hard problems are on a small, less expensive experiment, and then you know what those issues are, and you can plan for them as you build a larger, more expensive experiment. And so that's the exact principle that we're doing. Basically, the first thing we did is we built Aber 10 centimeter. Now we're in the process of building DM radio 50 liter, and I'll show you some photos in just a second. And we're about to start building this Cal experiment. The reason we have these two different sort of current scale experiments is this one is using that toroidal design, basically proving how we can scale up Aber 10 centimeter, whereas Cal is the first one that's going to be using a solenoidal design with this coaxial pickup and a coaxial tuning structure. And so Cal will allow us to reach these highest frequencies, whereas DM radio 50 liter cannot reach up this high. And then we have this plan for sort of two different experiments that will reach actually all the way down to this QCD band. DM radio meter cubed, which again has to be a solenoid because it's looking at the highest frequencies, and then DM radio gut, which is going down to this like especially well-motivated sort of gut scale axion space. But it's just a really, really hard experiment to build because we're talking about tiny, tiny, tiny GA gamma gamma. Okay, so this is, I'm gonna just show you two slides on what the 50 liter detector actually looks like. So this is the CAD design. So I think maybe 6 months ago, this is all I could have showed you. And now we have an actual detector, which is really exciting. We're in the process of commissioning it. And so you can see some of the components of the experiment. There's this, although this is cryogenics, this is the dilution refrigerator paired with a 4K cryostat. And then this is the toroidal magnet that's going to source our axion signal. This is currently in testing at the magnet manufacturer, so it's not actually coupled to all the sort of interesting readout that we'll have down here eventually. I quickly, during the last talk, put a note together about the challenges of actually scanning at these really, really low frequencies because it was talked about before. DM radio gut is at a really low frequency. So if you're thinking about actually bringing up a resonator at those frequencies, you have to scan really slowly. And that's one of the things that makes this experiment so hard. Not only are you looking for a really low GA gamma gamma, but you're also looking at really low frequencies. So if you think about the two ends of the frequency range for DM radio gut, going around 100 kilohertz to around 10 megahertz, if you do a little bit of calculation, you can basically see that you have many orders of magnitude difference in the scan rate that you can achieve at these two different ends. So when you're actually building the experiment, the vast majority of the time that you're going to be spending scanning is just to reach these really low frequencies. So just to think about the practicality. Okay, but there are some trade-offs at high frequencies as well. So as you're at low frequencies, you're spending a large amount of your time just ringing up your resonator. As you go to higher frequencies, you don't have to integrate as long, but every time you go to a different frequency step, you have to tune, you have to calibrate and make sure you're at the right frequency. That introduces actually a lot of dead time into your experiment. So the sort of best optimal regime where you're scanning the most frequency space at a time is actually somewhere in the middle. But sort of an interesting fact. Okay, so now I'm going to be talking about how we can basically scale these detectors up and the different technologies that are involved. So this is the figure of merit that we use for these kinds of experiments, is a scan rate. That's true for all different resonant experiments. This particular scan rate equation that I'm showing you is only applicable to lumped element experiments. There's a slightly different sort of set of parameters when you're talking about cavities, for example. So we can divide this scan rate up, so this is frequency with respect to time. This first part is all axion physics, so I can't control that. That's okay. Everything over here is stuff that I can control in my detector. Okay, so let's break down, I want to break down basically what all of these different parameters are and how we can improve them. But the first thing I want to note is that there's some weird exponents here that might be a little bit confusing. The reason why we have these weird exponents is there's actually two different pieces that are contributing to this B and V. So the first one, we have V squared V. This is the amount of stored energy in your magnet. The more stored energy in your magnet, the larger your axion signal. But then we also have this V to the 2/3. This is just an area term, an effective area describing your inductor. So if you have a larger inductance, then you have basically a better coupling of your signal into your detector. And so that's how you get these sort of weird exponents. Okay, so now looking at all of these different pieces, you can see that there's lots of different things that we can try to improve in order to reach a better sensitivity. So out front, this is what we call CPU, or pickup coupling factor. This is basically saying how efficient are we at coupling the axion signal into our detector. This maxes out at 1. Okay, so you can have maximally efficient coupling. So you can't get a huge boost in your scan rate by improving this, but you can hurt yourself a lot if you're not efficient. So you want to try and maximize this as much as possible. Here, that's that quality factor. So you want to reduce loss in your resonator. You want to increase the strength and volume of your magnetic field, also increase the inductance that you're using to read it out. And on the bottom, this is all the noise terms. So you need to get as cold as possible so that you're reducing your thermal noise. And you also want to reduce any added noise that you introduce with your amplifiers. Okay, so I'm going to talk about these technologies now. So the first thing I'm calling technology 0 because it's we can't really change it very much, is just getting cold. So there's a couple of reasons why low temperatures are required for these experiments. And this, again, this is true for higher mass axions as well. The first thing is that we use a lot of superconductors in our experiment because they have 0 loss. So the first thing you need to do is you need to cool below the transition temperature of your superconductor. That's actually not that hard. So niobium, the transition temperature is like around 9 Kelvin. Aluminum, it's around 1 Kelvin. That's okay. But generally, you actually want to cool well below that point. And I don't know if there's any sort of condensed matter thinking people in here. Does anybody know why we might want to cool well below the transition temperature for a superconductor? Yeah, so you do definitely want to be well below that transition point, but you actually want to be like an order of magnitude lower than that, which is well below the point where you're beyond that transition temperature. Band gap width. What do you mean by band gap width? So I'm not sure if this is quite what you're getting to, but basically there is a gap in the superconductor, which is when the amount of energy it takes to break your Cooper pairs into quasi-particles, and that is the thing I'm looking for. So basically, if you're at a temperature that's close to that transition point, you're going to have some thermal population of quasiparticles, and those can be a source of loss in your resonator. And so you want to reduce that population of quasiparticles as much as possible. Was that hand about the question, or do you have another question? Okay. Okay, so that's the most basic thing about why you want to cool down. But we have this fundamental limitation as well, which is that thermal noise is our absolute fundamental limit in how well we can do. And I'm going to talk to you more about this tomorrow when I talk more about sensors. But this means that not only do we want to cool an order of magnitude below the transition point of our superconductors, we actually want to cool down as far as we possibly can, because this will improve our ultimate sensitivity. And that's where we have that T in the denominator. That's where that's coming from. Okay, so how we actually do that, we use dilution refrigerators. They can get you down to about 10 millikelvin. This is a picture of a couple of the new dilution refrigerators in my lab. My students got really excited about naming our fridges after cartoon rodents whose names start with R. It turns out there's like 20 of these in the media. So this is Rita and this is Rufus. And so you can see we're very excited about these new fridges. This is a tradition of naming your fridge after something. And so we have ended up with rodents, which is amusing. I thought it was going to be like flowers or something when I started my lab. No, it's rodents. Okay, so that was technology 0. Technology 1 is magnets. So what are the things that we actually want out of our magnet if we're trying to have an axion search? Thoughts? High what? High constant, yep. Anything else? So the magnet itself doesn't need to be tunable. It can just be a DC field. It's the resonator that needs to be tunable. Yes. Yes, absolutely. Yeah. That's a really valuable veto for backgrounds. Yeah. Yep. So uniformity is useful because it helps us understand what the absolute value of our field is, but we don't need really, really high homogeneity like some condensed matter experiments do. Okay, that's pretty good. So these are the things that we need. We need a very large field. We need a very large volume. We want it to be stable over time with a known field pattern because we need to be able to make that translation to G gamma gamma, right? So we need to understand what the total field is that our axions are interacting with. The ways that we know how to build these lumped element detectors are in either a toroid or solenoidal form. So we want that kind of geometry. And then the other thing we need is we need some sort of low field region to put our sensors because superconducting sensors do not like magnetic fields. And so this is really easy, like I talked about with the toroid. All those fields are contained. This is harder with a solenoid. You have to do that on purpose, basically generate a region of low field. Okay, some of the considerations as you're building a magnet, I already talked to you about forces. Just to give you a bit of a scale of this DM radio gut magnet, the amount of sort of energy contained is about 1/4 of a ton of TNT. So this is something that is very serious. Like you really want to be thinking about safety as you design this magnet. Another thing to think about is quench protection. So I sort of mentioned this briefly, but basically, if you, for some reason, go from a superconducting state to a normal state, you have to dump your current somewhere. This is not something that is abnormal to have sort of like a power blip or something like that. If your fridge heats up, say because the power goes out, your magnet is going to go normal. And so you have to have safe ways of dealing with those very large currents and the very large forces that are going to be happening as suddenly those magnetic fields are going away. You also need to consider what materials you're using to design your magnet. And I'm going to talk more detail about this in just a moment. But basically, there's a bunch of different parameters that describe how strong of a field you can have, the critical temperature, critical field, and critical current density of the materials that you're using to actually build your magnet. And then the last thing is that magnets are often half the cost of an axion experiment. So these are a very, very large fraction of the cost, which means that you need to be really deliberate about the choices that you make as you build your experiment, so that the cost doesn't just run away. Okay, so now I want to talk to you about materials. I realize that this is a mostly theorist audience, which is you should be thinking about materials. They're really important. So the first thing that you might think about is just using an iron magnet, right? That's the most simple thing you could do. But the problem is that iron is not a very good material if you want a really, really high field. It saturates at about 1 to 2 Tesla. You could put a coil to try and get it up to higher field. But it also is just really large mass. So it's not something that you could put inside your cryostat when you're talking about these really large experiments. And so you need to build something even bigger so that it can be sort of on the outside of your cryostat. And the other thing is, like you said, you can't ramp down an iron magnet. If you have a coil along with it, you could ramp down the coil, but you can't ramp down that magnet. So it also means that it's more challenging to actually work on your experiment, because anytime you're working on it, you'd have to be working in a region of high field. Okay, the material that most magnets are made out of, or most superconducting magnets are made out of, is niobium titanium. This is a really, really nice material for building magnets. It's really easy to make into wire, and it's relatively cheap. So this is what a cross-section of some niobium titanium wires looks like. So you can see basically there's these little filaments of niobium titanium, and they're stabilized inside this copper matrix. And that copper matrix is really useful because it helps get rid of heat. It's good in the case of a quench. You can have the currents go into the copper instead of being all inside the nib tie. And it also, again, helps you make these like nice flexible wires for winding. Nib tie is really the workhorse of a bunch of different things. So it's the workhorse of accelerator magnets, of MRI magnets. It can get you up to pretty large fields. In practice, you can have nib tie magnets up to around 9 or 10 Tesla, although the critical field is a bit higher. That's true for all of these magnets. Basically, you can have a critical field that's much higher than the standard operating field, because you don't want to have a small blip basically put you over the point where you're going to quench. So you operate significantly below that critical field. And most axion experiments use nib tie magnets. Okay, but as you're scaling up, this might be an issue, that you can only reach those field values. So there's been more work recently about thinking about what kinds of materials you could use instead in order to reach higher fields. So niobium-3 tin is a really, really good choice. It is now slightly more standard, although again, not as standard as nib tie, and it can reach fields all the way up to around 16 to 20 Tesla. The problem with niobium-3 tin, when you're actually building a magnet, is that you can't make nice wires out of it. So it's just a very brittle material. So it's sort of interesting. How you actually build magnets out of it is you have this bronze matrix with a bunch of niobium filaments inside it. That you can make into a wire. So then you wind your magnet, and then you actually bake this entire structure up to a very high temperature. And what that does is it reacts the niobium with the tin. And so you can see here is an example cross-section. Once again, you have these filaments inside a matrix. But if you look, basically there's these cores where the niobium didn't react, and there's these sort of edge areas where you have that reacted niobium and tin. And so most of the current is going to be going through those little sort of rings around those filaments. And then just one thing to note is that this ITER fusion tokamak, they're using niobium-3 tin in order to reach the really high fields that they need in order to do fusion. Okay, then the last material I'm going to talk to you about is high temperature superconductors, which are really, really cool, but also really expensive because they haven't been around as long, and there's just not as much in production. There's several different materials that you can use that are high temperature superconductors. The most common ones to make magnets out of is what's called REBCO, or rare earth barium copper oxides. The record, I think it was set either earlier this year or last year, for a REBCO magnet was a stunning 48.7 Tesla. That is huge, huge field values, but this is the magnet. And so you can see that there's a chemical bottle for scale. So this is really, really tiny volume. So not very useful for axion experiments, but a really impressive demonstration that you can build these things up to incredibly high field values. Now, one thing to note is typically you don't actually have just REBCO when you're building a magnet that goes up to this field. You have these various inserts. You have an insert of REBCO inside maybe a niobium titanium magnet or something like that. So basically the reason that these materials can get up this high is they have both a high TC and a high critical field value. So you can operate warmer, or you can still operate cold and then drive your current up really high, because basically it's always a trade-off between how much current you have, what the temperature is, and that kind of thing. This is also harder to wind than something like a niobium titanium magnet because it comes in these tapes. These are not very stable materials, so you have to sort of have all these different layers to make them structurally sound. Something that's weird is that these are not normal superconductors. They don't follow standard BTS theory. I'm forgetting the initials. BCS theory. And so they don't quench in sort of a standard way. The hotspots don't move around quickly. So that's something that has to be figured out as we build these very high stored energy magnets. And like I said, they're really expensive. I actually have a whole slide on this because this is, like I said, really critically important as you're designing these really large scale experiments. So the standard unit that you use is the sort of price per kiloamp meter. So this is how much current it can hold and how long your wire is. As a comparison, nitrogen titanium, $1 per kiloamp meter, $8 per kiloamp meter. And right now we're talking about something like $800 to $1,200 per kiloamp meter. So these are really, really expensive. But they get you to these really incredibly high fields. And I read one analysis which said that in order for this kind of material to be widely adopted in sort of standard magnets, you need it to drop an order of magnitude or two. Yeah.
They have like the short time scale with negative, right? Like they're not always for that extent. Is that a fundamental thing or just because of what they need?
I don't actually know much about how they operate, but no, you can operate these for a long time. Yeah. Okay, and then I got really into the weeds when I was putting this slide together, and I found a bunch of cool plots. So this is an analysis of the different prices. So you can see at the beginning it was really expensive. And so back in 2010, when they had this paper, they had a prediction that by 2021, the price would have dropped to $35. In 2021, this is actually a lower number than this one, but depending on where you're buying it and what kinds of tapes you're using, obviously it's going to be a different price. And so my message here is we should build more Axion magnets because the more production there is, the more the price will drop. So let's build lots and lots of Axion experiments out of HTS. Okay, so how much would an actual magnet cost? Yeah, so a reference point, so I recently bought a 9 Tesla magnet that has a 15 centimeter bore for my lab, and that was about $200,000. But that's the Cal experiment, so it's like it doesn't reach QCD Axion space. When we were doing costing for the meter cubed magnet, again, nib-tie, that was going to be about a $10 million magnet. We haven't costed yet. It's still, we'd have to figure out what materials we're going to use and what the actual specs are. The funding agency, hopefully. But again, if you think about the cost of an Axion experiment compared to the cost of something like a WIMP experiment, this is tiny. Existing WIMP experiments are order hundreds of millions of dollars. This is an order of magnitude lower, and in my mind, we're getting more science, depending on who you talk to.
Space.
That's super, super expensive. Yeah. Okay. Oh, sorry. Any more thoughts on the ridiculous price of magnets before I move on? It actually is a problem, yeah. And so one thing, I don't know exactly how the funding works in Europe, but in the US, basically there's different portfolios for different size projects. And so these Axion experiments actually fall below the threshold for being an official project, which is challenging because it's really hard to be in this space in between. We're not R&D, we're too expensive for R&D, and we're too cheap to be an official project. And so this can be actually a hard space to be in, sort of weird. Okay, so like I said, so far, all of the experiments are niobium titanium. And so this is just a view of a bunch of different of the DM radio program magnets. You can see right here, this is about the size of a large grapefruit. 1 Tesla magnet. DM radio 50 liter, which we're about to start running, is larger. It's like this large, similar field strength. And then, like I said, we just got a 9 Tesla magnet for my lab with a smaller volume. This is a solenoid. This is how we're going to do the Cal experiment. And then we have ideas for how we can scale up for the DM radio meter cubed magnet. Still 5 Tesla, totally within the range of nib-tie. You can use those nice cheap materials. As you scale to a much larger experiment, you can no longer use that. You really need to be thinking about using either -310 or, or HTS. And so we did this study where we figured out what sort of the baseline needs are for R&D for all of these different components. And you can see that you really need, this is just a scaling argument, so this is not the definitive numbers, but you can see you really need something that's of the scale of between 10 and 20 Tesla and a 10 meter cube volume. And so, yeah, you need sort of advances in technology and cost reduction. One thing to note about this particular study is that you can see basically if you don't do as well, like maybe you have to have an 8 meter cube magnet or something smaller volume, you can make up for that and still reach the same sensitivity by, say, improving something like your sensor performance. So this is still future, we need to do R&D, but we have paths to get there. For scale, this is what the DRAM radio gut magnet looks like, much bigger than the original grapefruit size magnet. Okay, and then I again just wanted to note basically this is very synergistic with some of the R&D for both accelerator magnets and fusion. So the gut scale magnet, this is something that's right on par with existing fusion magnets. Okay, so I'm running out of time, but I just want to sort of, maybe I'll pass through this quickly, basically saying we also need to do R&D for tunable resonators. This affects all of these different components, how efficiently we couple, the quality factor, and also the inductance of our system. Again, we need low loss, high quality factor. The best thing you could do would be have a superconductor, but that may not be possible if you're operating in magnetic field. And so what you need to do is basically fastidiously separate your resonator from the outside environment because that will cause loss. Another big challenge is tuning because this is all happening in a cryogenic environment. At the base stage of a dilution refrigerator, you have microwatts of cooling power. And so that means any tiny amount of friction is going to quickly swamp the amount of cooling power you have. Okay. I think I'm going to skip through here. Okay, yeah, so I'll just flash some pictures. So this is a fixed frequency resonator that our collaborators have demonstrated at Princeton. They were able to achieve a quality factor of 2 million using this resonator. So you can see here is an inductor. So there's wires wound around here, and this is a parallel plate capacitor. The next challenge is basically taking that and seeing if we can maintain that quality factor, both as we move into the real experiment where things are more the sort of environment is more complicated, and also adding in tuning. Because when you add in tuning, you're going to again have to have some lossy materials in order to both have motion and also cool things down. Skip this as well. Okay, so I promised you that I would talk to you about active resonators. This is the idea of Bode-Fano evasion. So the Bode-Fano, oh, I think my picture disappeared. Oh, no, okay. So the Bode-Fano limit is basically what's saying that you cannot do better than that quality factor bandwidth that I told you about. So let me just actually, I'm gonna have all the pictures up. So basically you can either have this dotted line or this dashed line. You can either have something where you don't have a very high enhancement, but you have large bandwidth, or you can have a larger enhancement with a smaller bandwidth. And so that's the limits of having this passive resonator. But if you're able to remove some of these criteria, either a passive resonator, something that has linear elements, so if you can add in nonlinear elements, or if you can change time invariance, then you can potentially have a larger bandwidth while still maintaining a high enhancement. And so some collaborators at SLAC are working on how to do this using Josephson junctions, because these are nonlinear elements. And so they're basically violating one of these criteria in order to see if they can do this. Now, this is still all very, very early work. So we don't know if we can do this. We're basically developing both of these R&D paths at the same time. Better passive resonators, and also seeing if we can do active enhancement. Okay, the third technology in this program is quantum sensors. So basically figuring out how much you can drop this added noise from your amplifiers. This is going to be the topic of the next lecture. I'm going to be talking almost exclusively about this. So I won't talk about that now. And then last 5 minutes, I'm going to tell you about superconducting radio frequency cavities. So the basic idea here is when you're building an accelerator, you have a bunch of cavities that are used to accelerate your particles. And in order to have a really good acceleration, they have done a lot of work to improve the quality factor of these radio frequency cavities to the point where they can get quality factors of something like 10 to the 11. This is just absolutely crazy. And so when you're thinking about an axion experiment and you're thinking about an enhancement of 10 to the 11, like amazing. You absolutely want that. And so I think that a lot of this came about because people were like, okay, what can we actually do with these really high quality factors? There are a few different ideas. I'm going to tell you about one of the things you can do with them, which is this heterodyne approach. So once again, we're at low frequencies. We don't want our axion wavelength to be tied to the size of our cavity. We have to build a really big cavity, and all of that nice R&D for these superconducting radio frequency cavities goes out the window because they've been developed on a relatively small scale. So instead of having the the scale of your cavity tied to your axion mass, you can have that axion mass tied to the difference between different modes in your cavities. So if you have a gigahertz cavity, and you have two different modes that are offset by, say, a megahertz, instead of having a passive B field, you can pump an RF tone into your cavity at one mode, and then see if you have power in the other mode. Right? Okay, so it's that difference frequency that you're looking for. So just a bit of a comparison between the lumped element method where you have a static B field and this method where you have an RF tone. Here, this is for the lumped element method, you have this static tone here and you're looking for a tone at the frequency of the mass of your axion. That's that difference. Here instead, you're pumping at some omega 0 and you're looking again for a tone at a different frequency, but here omega 1 is now the original tone omega 0 plus MA. The power of your signal has sort of similar scaling where you have, this is the energy stored in your magnet, and you have these sort of axion physics factors out front. And then once again, it's dependent on the quality factor of your, this is the mode of your signal. So this is your omega 1 mode, not your omega 0 mode. And so when you think about the amount of power that you can have in a signal, the amount of signal power you have in this kind of experiment, you're not able to get to quite as high V naught. So we're able to make really, really large static magnetic fields. You can't really make the same level of magnetic field with this RF tone, but you're able to get a much higher quality factor. So basically you can see how you can trade off between these two different parameters. This is one example of an experiment that is doing this. This is Shade. This is at Fermilab. So they've done some initial measurements. They haven't actually done a search yet, but you can see this is a real cavity. So when you're thinking about making an RF cavity for an accelerator, you basically have a bunch of stacked ones of these. And so you basically are rapidly changing the RF tone to drive charged particles across this. But instead, you can use it for an axion search with just one. When you do a simulation of the modes inside your cavity, basically you can have, this is a simulation of the pump mode, and this is a simulation of the signal mode. Now, if you just have a static cavity, that will have one frequency that is the offset between those two different things. But you can tune by mechanically changing your cavity. So this right here, you can see these green elements right here. You can squeeze the cavity itself and change the offset between these two different modes. Now, at first, it might seem like it's hard to tune over a wide range of masses, but the thing is that because these are gigahertz cavities and you're tuning over kilohertz and megahertz frequencies, it's not actually that much difference in the sort of the shape of your cavity in order to get that tuning. Now, actually implementing that tuning is challenging, but you can get that sweep over a wide range of frequencies. And then you also need some sort of coupler ports, both to inject your tone and to read out in your other mode. There are a lot of challenges here. This is a much more sort of new idea than these lumped element experiments. They haven't existed for as long. And so there's still a lot of things that need to be figured out. So I told you that tuning is something that's always hard. And so they're working on basically having reliable tuning and calibrating what their modes are. A thing you really want to worry about is if you have any leakage between your pump mode and your signal mode. And so that's something that they've seen with these initial experiments. So there is some leakage, which you don't want, right? Because that is the exact same as your axion signal. And some of the ways that this might be happening is if you have vibrations of your cavity or any sort of microphonics that are happening. I put a couple of different reach plots here. This is the sort of initial idea plot showing that you can actually reach down into this QCD axion band, although not all the way down into the nano EV. This is one of the more recent papers that I've seen, which is updated with sort of realistic systematics for an experiment. And so it doesn't look quite as impressive now, but maybe they'll come up with ways to beat down some of these systematics, and they'll be able to get a better reach later. Okay, so just barely on time, a review of what we covered today. So we talked about the expected signal from dark matter and how there's these different detection regimes where you need different methods in order to search your space. We talked about why you want to look for low mass axions. There's a bunch of different theoretical reasons why you might prefer a low mass axion. And then we talked about how you can use lumped element detection with LC circuits and some of the technologies that go in to building those experiments, and then closed up with another method that you might be able to use to look for low mass axions. How does what? How does it accelerate? Accelerate? I don't know what that shape is, the accelerator. Are you talking about this like D-shaped coils in a toroid? I think this is maybe. So I have never tried to design an experiment for this design, but it does look like it would be very similar to a toroid in that you have. I believe it's still basically a toroid though, right? The magnetic field is going around like this. It's just sort of a different shape. So I think you would still have the same, you'd still couple to it the same way you couple to a toroid, where you'd have sort of a low magnetic field region in the middle. But we don't need any sort of fancy field shaping. If they're cheaper though, I mean, we could, I don't think they are. Yeah. Yeah. So we call it amplifiers, but they are still using sensors that may have some amplification effects. So you can think about like scintillation or something. So you have some energy deposited and then you have a bunch of light that comes out of it. So it's a totally different signal mode. So maybe like an avalanche photodiode. Again, you're having this effect where you're taking a small signal and you're making it bigger. But for us, it's in the, we call it an amplifier because it's really just a circuit element. And part of the reason for that is we have these really, really low energy signals, right? So you have to amplify it to read it out with normal electronics. Does that answer your question? Okay. So another actually example of a sensor that I work on for higher mass things is a qubit-based sensor where we amplify a quasi-particle signal. We don't call it an amplifier, but it does amplify the signal. A PMT is a great example. Yeah. Yeah. So if you've seen those beautiful pictures of the big like neutrino detectors that have all these, we can pull it up at some point. You should look them up. They're really beautiful and very like historic technology. Yeah. Compared to super CDMS, you said? Yeah. Mm-hmm. Yeah, so you could, so like I said, one of the backgrounds we had was radio signals. You could imagine if you had one detector in Boston and one detector in California, you would not have the same radio signals. So that would be a way of vetoing those signals. But it's not, you don't have the same sort of fiducialization that you can get by having, like for super CDMS, where you have lots of towers, or for LZ, where you like get rid of the stuff on the sides. It's just a different kind of background. So you want to reject it in different ways.
But if you like weaken the magnetic field, right, look on a signal, you can now see, oh, the amplitude is weak, right? That's
Yeah, right. We have other handles to reject backgrounds. Yeah. Yeah. So I think I have a. Oh, there it is. So you can see, so it's about a 10-liter solenoid for the one in my lab. This other one that we're doing is about a 50-liter volume. Ah, yes, let me go to that scan rate equation. Wait. Oh no, I'm going the wrong direction. There we go. So there's that V. So it comes in with the stored energy of the magnet. And then this is an effective volume, which is the inductance. Yeah. It's the range of the, how do we pick the range that we look over? Is that what you're asking? Yeah, right. Okay, yes. So part of it is practical considerations. So for example, in the 50-liter, I think it's earlier. Yeah, here. So in this 50-liter experiment, you can see that basically we have the magnet up here, there's an inductor here, and then we have to have our tuning elements down here. And so a fundamental restraint, not fundamental, but like a practical restraint is that you have to fit your tuning element inside that box. And so that you cannot have a capacitance really, really large because it just won't fit inside that box. So that will tell you the sort of lower limit of the frequency that you can reach. That's the sort of hardware aspect of it. You also have what I talked about with this different sort of scan rate consideration. So as you go lower in frequency, you have to ring up your resonator for longer, so it's slower. As you go higher in frequency, you have more dead time because you spend more time calibrating. And so when you're picking your first frequency to start at, it's some combination of what is an easy resonator to build, what can we scan the fastest, and then ultimately you want to scan over a very large range. Now, as Sergi was talking about, if somebody told me exactly where the axion was, we would design our experiment to look for that frequency, but we don't have that. So we just have these practical considerations for, because ultimately we want to scan the most area on that plot. And so we pick where we can scan the most area fastest first. Spring. Those will be fixed frequency results, so it'll just be at a single frequency, and then we'll add the tunable capacitor in. But yeah, spring. We're still finalizing it. It's probably around 70 kilohertz. So if you want to design a theory where we have a 70 kilohertz out, please do. We can cite it. Oh yeah, I think in terms of frequency. So 70 kilohertz is, yeah, wait. Yeah, roughly. Yeah. Yeah, so you want to make sure you're at least integrating long enough to have a full coherence time, but typically you integrate longer. The amount of time you integrate is dependent on how low you want to reach, but your sensitivity only goes as time to the 1/4 power. So integrating for a lot longer doesn't actually get you a lot more sensitivity once you go beyond the coherence time for your signal. So Abracadabra ran for about a month overall. Yeah. And I think these projections are, I believe the meter cubed one is 5 years. This one is sort of notional, but roughly 3 years. The idea for a 50-liter is we will actually swap out our sensors partway through to do some R&D for some of the quantum sensing techniques. So I wouldn't think too much about what the sort of total scan time is for this, but this one is about 5 years. This one is also for about a month.